let's begin our discussion of mathematical induction. Induction is used to prove statements of the form for all natural numbers n, S of n. Now, there are two parts to a proof by induction, and both parts that I will mention are needed. Otherwise, you haven't proved the statement. Okay, well, part one. This is called the basis step. And then part two is called the inductive step. In the basis step, we verify that S of 1 is true. This is usually straightforward, but it is also, like I said, part of the proof. Now, in the inductive step, this is for k, a natural number. We prove an implication. We prove that S of k implies S of k plus 1. It's an implication. So what does this mean? Well, we assume, in other words, for k natural number, we assume that S of k is true. And then we show, based on this assumption, that S of k plus 1 is true. And this part, the assuming S of k is true part, has a name. This part. This is called the inductive hypothesis. Now, once you have done the basis step and the inductive step, you have proved S of n for all natural numbers n. Well, why is this the case? Okay, S of 1, you have verified S of 1 is true. And then you could start marching through this. So S of 1 is true. Well, you've shown this implication. That means S of 2 is true. Okay, now S of 2 must be true. You have shown this implication. S of 3 is true. Okay, now you have shown, right, S of 3 is true. You have proved the implication. S of 4 is true. And this continues. Then you would have S of 5, S of 6, S of 7, S of 8, until this would sort of march up and you would have it proved for all natural numbers n. This is the idea of induction. Now, before we do an example, it's important to understand what this inductive step is not. You are absolutely not assuming the statement is true for all k. So we are not assuming S of k for all k in this step 2. And this is an important thing to realize because that's what you're trying to prove. So you wouldn't be assuming what you're trying to prove. That wouldn't be a sound proof technique. What you are showing in this is that if it happens to be the case that S of k is true, it must follow that S of k plus 1 is also true. And that, together with this basis step, like I said, would allow you to march through all of the natural numbers and see that S of n would be true for all n. Here's my first example. We want to prove for natural numbers n, if we add I equals 1 to n, this, to I minus 1, we get n squared. Now, we can think about what this is saying, right? When I equals 1, this is 1. When I equals 2, this expression is 3. When I equals 3, this expression is 5. So what this is saying is, if you add the first n positive odd integers, we get n squared. That's what this equation is saying. So now let's prove this using induction. And like we just discussed, we have two steps. The first step is a verification. We want to make sure it holds for n equals 1. The left-hand side, well, this has only one term. It's a sum. I goes from 1 to 1 of 2i minus 1. This is just 2 times 1 minus 1, which is 1. And then the right-hand side is 1 squared, which is 1. Okay, so we have 1 equals 1, and so everything is wonderful for our basis step. Now comes the inductive step, and we must clearly state the inductive hypothesis in our inductive step. So let's assume we have a natural number k with, well, it would be this holds for k. I equals 1 to k of 2i minus 1 is k squared. We want to show the statement holds for k plus 1. So I will write this. We want to show I equals 1 to k plus 1 of 2i minus 1 is k plus 1 squared, period. Now start a new sentence, okay? I'm now going to work with this sum I equals 1 to k plus 1 here, but I don't want to just keep working on this. This was a sentence. This is what I want to show. Now I start a new sentence to actually show it. Well, I will need to use my inductive hypothesis. This is always part of an induction proof. So you see what I can do here. The first k terms here, I know what the sum is. So let's break them off. This would be equal to a sum up to k of 2i minus 1. And then plus, well, evaluate this at k plus 1. This would be 2k plus 1 minus 1. This here is equal to k squared. Okay, and then I have the rest of this, which is 2k plus 2 minus 1 using the inductive hypothesis. That is where I used it, here to here. And then finally, we're almost there. This is k squared plus 2k plus 1, which is exactly k plus 1 squared. And I would just end by saying, as desired, put a box, because I clearly stated what I needed to show, that this sum is equal to this, and then I showed it, so this completes this proof by induction. Here's my next example. We will prove for natural numbers n is less than 2 to the n, using induction. Well, our basis step will be for n equals 1. We verify. Well, the left-hand side is 1. It's just n. And the right-hand side is 2 to the 1, which is 2. And it's definitely the case that 1 is less than 2. Okay, so this is all that I really need for my basis step. Like I said, it's typically a verification. Now for the inductive step, we assume we have a natural number k with k less than 2 to the k. And then we want to show that k plus 1 is less than 2 to the k plus 1 using induction. Okay, we have k plus 1. Well, this is equal to k plus 1, so this is less than 2 to the k plus 1. And this is where I used the inductive hypothesis right here. K is less than 2 to the k. Now, what I want is k plus 1 is less than 2 to the k plus 1, and I don't have it just yet, but I almost do. So k is a natural number, meaning the smallest it can be is 1. So this 1 here is certainly less than 2 to the k. Now, well, I have 2 to the k, so this is equal to 2 times 2 to the k, which is 2 to the k plus 1. So if you follow, we have a string of less thans and equals. Altogether, we see k plus 1 is less than 2 to the k plus 1, as desired. And this is the end of this proof by induction. Here's my next example, and you might recognize this. We had this combinatorial identity as one of the homework exercises back when we were working on combinatorial proofs. And you could, and we did, certainly prove this using a combinatorial proof, but now I want to prove this by induction. We can definitely use induction here, and we will. In our basis step, we will verify for n equals 3. The left-hand side, this is 3 choose 3, this is 1. And the right-hand side, if we have n equals 3, is 4 choose 4, which is also 1. Okay, so we have verified. 1 equals 1. Everything is wonderful. Now comes the inductive step. We assume k is an integer bigger than or equal to 3, and we assume that this 3 choose 3 plus 4 choose 3 all the way out to k choose 3 equals k plus 1 choose 4. We want to show if we go out to k plus 1, we would get k plus 2 choose 4. We have this 3 choose 3 plus 4 choose 3. Well, the one right before it is k choose 3, and then we have k plus 1 choose 3. So this is the left-hand side of this that I'm trying to show. Now, here is where we use our inductive hypothesis, because this part is here. And so these terms add up to k plus 1 choose 4. So this underlined in green is k plus 1 choose 4, and then we just recopy this one term. And this is where I used the inductive hypothesis. K plus 1 choose 4 plus k plus 1 choose 3. This equals k plus 2 choose 4. This is using Pascal's identity. This was the identity that we saw in chapter 3 that gave us really that the Pascal's triangle is made up of binomial coefficients. It came from this identity holding. Well, you see, this is what I wanted. I wanted this sum to be equal to k plus 1 choose 4. So I can just say as desired. And this completes the end of this proof by induction. We prove this combinatorial identity using induction. Before we move on to the next example, I want to just make a comment, and that is we may use induction to prove statements of the form for all n in A, S of n, where A is, well, you can take integers that are bigger than or equal to some number, and here B is an integer. And this is what we saw in this last example. We proved that combinatorial identity for integers n bigger than or equal to 3, that was the B, but you can really start anywhere. Of course, if this B is 1, then this is natural numbers, and that's exactly how I first stated induction. The only thing that changes if you start at -10, or if you start at 115, or 0, or some other integer besides 1, is just this smallest integer you're trying to prove something for. This is what you check in your basis step. And then the rest sort of goes the same way as we have been doing. But I think this comment is important because sometimes the statements are not just stated for natural numbers. Okay, now for our next example. Let's prove this sum, adding up these powers of 3. This equals 3 to the n plus 1 minus 3 over 2. And this is for natural numbers n. Again, by induction. N equals 1. Well, the left-hand side, there will just be, this is a 3 to the 1. This is 3 to the 1. And the right-hand side, this is 3 squared minus 3 over 2, which is 9 minus 3 over 2, 6 over 2, which is 3. And everything works out for our basis step. Now for the inductive step. We assume k is a natural number with, well, we will have 3 plus 3 squared out to 3 to the k equals 3 to the k plus 1 minus 3 over 2. And then we want to show 3 plus 3 squared out to 3 to the k plus 1 is 3 to the k plus 2 minus 3 over 2, period. Now, start a new sentence. This is important. We have, and then I will start a new sentence to actually show this. I mentioned this before, but I have had many students that they will start well, where they start, assume k is a natural number with this holds. Okay, wonderful, inductive hypothesis. But then, instead of writing show, they just write this equation. And it looks, first of all, like, are you claiming it's true? Because it's not clear. You haven't stated that that's what you're going to show, and you have not yet established it. But on top of that, they'll have this equation, and then they just start working with both sides and hoping to match something up. And that is very hard for your reader to follow. So if you have not yet established, which we have not yet, right? Not for k plus 1, state that you are going to show it and then start a new sentence to actually show it. And you want to work with just one side of the equation until you arrive at the other. That is how I've been doing these, and that is very easy for your reader to follow. Okay, so we have, I will write the kth and then k plus 1. And here is where we use the inductive hypothesis, as we have more than one time. Let's see, there's a plus here. That the first k terms here, they equal this. So this is 3 to the k plus 1 minus 3 over 2. And then we just have this one term still to write. And this would be using the inductive hypothesis. Now, We can use this as guidance. This is another reason why it's very nice to write what you want to show, because I know I need 3 to the k plus 2 minus 3 over 2. And I have an over 2 here, so I will get a common denominator and then add. This is 3 to the k plus 1 minus 3 over 2, and then plus 2 times 3 to the k plus 1 over 2. Now, 2 of these terms, this one and this one, I can factor out a 3 to the k plus 1. So I have 3 to the k plus 1 times 1 plus 2, and then minus 3 all over 2. This is 3 to the k plus 1 times 3 minus 3 over 2. Now if we multiply, right, this is a 3 to the 1. We would add the exponents, and altogether we have 3 to the k plus 2 minus 3 over 2. And this is what we want to prove as desired. And this is the end here. We have completed this proof by induction. This will be my last example for today. For natural numbers n, let's prove 3 divides n cubed minus n using induction. I like this example because it's a little bit different than the ones we have been working on. The basis step, we need to verify this is true for n equals 1. 1 cubed minus 1 is 0, and 3 divides 0 as 3 times 0 is 0. So we have verified the basis step. In the inductive step, let's assume k is a natural number with 3 divides k cubed minus k. And then we will show that 3 divides k plus 1 cubed minus k plus 1, like this. But before I jump into this part, let's unravel our inductive hypothesis. The inductive hypothesis really says the following, that there exists x and z with 3x equals k cubed minus k. This is our inductive hypothesis, right? That's exactly what this means. Then, well, I want to say something about k plus 1 cubed minus k plus 1. And if we remember our binomial theorem or Pascal's triangle, and we have used this more than one time this semester, the coefficients here will be 1, 3, 3, 1. So this would be k cubed plus 3k squared plus 3k plus 1, and then minus k minus 1. Okay? This equals, well, I will group k cubed minus k together. And then I have this 3k squared plus 3k. But then I have plus 1 minus 1, which adds to 0. So far, you notice I have not used my inductive hypothesis. I just rearranged some things. But here is where I will use this. K cubed minus k is equal to 3x, where x is an integer. So this is 3x plus 3k squared plus 3k. And now you see I am basically finished. I factor out a 3. This is x plus k squared plus k. And as x plus k squared plus k is an integer, we see that 3 divides k plus 1 cubed minus k plus 1 as desired. And this will complete the end of our proof by induction, this example here.